We're now going to take a look at how Lewis structures that we learned how to draw in a prior video can be used to predict the three-dimensional structures of molecules. In order to use our Lewis structure, which is a two-dimensional drawing of molecules, to predict the actual three-dimensional shape of a molecule, we're going to have to utilize a theory that's called VSEPR, or VSEPR. And that stands for Valence Shell Electron Pair Repulsion Theory. The idea is that if you have pairs of electrons, because they're all negatively charged, so by electrostatics, they're going to repel each other to the maximum distance possible. And so whatever shape you end up getting when the electrons are as far away from each other as possible, that will be the molecular shape of that species. And so we can take a look at methane, which is CH4. If we were to draw the Lewis structure, it's going to look exactly like this, just a cross or a plus sign. And that's because we're currently drawing it as a two-dimensional structure. And with that particular drawing, we see that the angle between the hydrogen to the carbon to another hydrogen is 90 degrees, and that's the best we can do in two dimension. But remember that these molecules are three-dimensional, so they have the ability to separate even further because they have another dimension to work with. If you have a molecule with 4 bonds like this, then they can actually separate out using the structure that's called a tetrahedron, and that angle between the H to the C to the H is going to be slightly bigger than 90 degrees when you separate them out in 3 dimensions. That's the main idea about VSEPR. The shape that you're going to get is the shape that allows the maximum separation of the electron pairs that you have. I want to illustrate the idea of VSEPR for how the electrons will repel each other and how specific shapes would be formed as a result of those repulsion. So let's say you have a molecule that has 2 electron pairs. They're both bonding pairs in this case. So there is a bonding pair on this side and there's a bonding pair on this side. An example of this would be BeF2. Now, of course, we don't have to draw them straight like this. We could have the other bond go up 90-degree angle. But remember that the whole point here is the electron pairs, which is this pair and this pair right here, are trying to be as far away from each other as possible. So let's try to move this shape around to see if we can force the electron to be closer together. So you can see that if I try to make smaller angle compared to this 180 angle, I can't, because that other electron would automatically be repelled to go further. And that's exactly what's happening in a real molecule as well. The electrons are not going to want to be closer than this 180 degrees angle right here. That is a shape that we will see when we have a molecule with 2 pairs of electron around the central atom. That particular structure is what we call the linear structure, and that's what we refer to as the electron geometry for the molecule. So any molecules with 2 pairs of electrons around the central atom is automatically going to adopt a linear electron geometry. So let's say I have 3 pairs of electron around my central atom. So let's make that third pair a bonding pair also. So you notice as soon as I added that third bonding pair, the angle changes. It's no longer 180 degrees, because if this were 180 degrees, then the angle there would be 90 degrees. As soon as I try to force the angle to be smaller, then the electrons would be repelled. Well, if you look at the shape here, this is the shape of a triangle, so the angle here must be 120 degrees. That's exactly what it is, because it's shaped like a triangle and all the atoms are on the same plane. We call this Trigonal Planar. That's the electron geometry. Anytime you have 3 pairs of electron around the central atom, then that structure would be the one that we would expect to see. If we go to 4 electron pairs, remember that that was what we talked about in the case for methane. There's 4 different pairs of electron. Because we're in 3 dimensions, the atoms can go in the front and the back of the plane, as well as the X and Y plane. And so you can see that the angle here is a little bit bigger than 90 degrees, and that angle is 109 degrees 0.5. So that's what we would get if we have 4 pairs of electrons around our central atom. As I mentioned to you earlier, this is what the shape of a tetrahedron would be. So we call the electron geometry tetrahedral. Right now, what we're talking about is everything having bonding pairs around the central atom. Well, it's not always going to be the case. This is an example for methane, but if you look at the example for ammonia, whose structure is shown right here, you notice that around ammonia we still have 4 pairs of electrons. So there's 1 pair here, 1 pair here, 1 pair here, so 3 bonding pairs, and then 1 that is lone pair. So ammonia still has 4 pairs of electrons around it. How would that structure look like? Going back to our model, anything with 4 pairs of electron automatically has to have that tetrahedral electron geometry. So whether the 4th pair is a bonding pair or the lone pair, it will still have a tetrahedral electron geometry. So now what I have is the same structure, but instead now I have a lone pair around that central atom. So you still have that angle of 109.5. In fact, for ammonia, the angle would be a little bit smaller because hydrogen is a small atom, and then there's a larger repulsion between lone pair and bonding pair. But the ideal bond angle is still 109.5 here because it's still a tetrahedral electron geometry. Now the difference, of course, is that when you look at the structure of ammonia, you can't see that lone pair because a lone pair is a pair of electrons that's part of that atom, that central atom. So all we can see is these 3 bonds right there. So you can see now if I take out that lone pair, the lone pair is still there, it's just part of that atom. So this is the actual structure of ammonia. So if we were to do an experiment, that's what we would see. The question then is, what would we call this structure? We can't call it tetrahedral because tetrahedral means that it has another thing sticking out on this side. So what should we call it? That's when we need to come up with a different name for it, which we call the molecular geometry. Is the name of the shape that we actually see. The electron geometry is the name of the shape based on the number of electron pairs that are around the central atom. And since there's 4 electron pairs, including that lone pair, we still call it tetrahedral. But the molecular geometry, because all we can see is the bonding pair around the central atom, so we would call this Trigonal Pyramidal because it has the shape of kind of a flat, low pyramid with a triangle base. Okay, so in the discussion we just had with the simulation, I showed you how a molecule might have different electron and molecular geometry. So the electron geometry is just how the electron pairs are arranged, and that counts both bonding and lone pairs, whereas the molecular geometry only counts the bonding pair and how they're arranged in 3 dimensions. I want to point out that when you have a double bond, you count that as one effective bond for the purpose of assigning the geometries for VSEPR. So for example, if you have the structure of CO2 in this case, in theory you have 4 bonds, 1, 2, 3, and 4. And you might think that if you have 4 bonds, that should be a tetrahedral structure. But in this case, because the 4 bonds are really arranged in a linear shape, the structure of CO2 is linear. So in order for VSEPR to help us account for the linear structure, we count those 2 bonds as one pair of electrons. So this is a pair and that's a pair, so that means you have 2 pairs of electrons. 2 pairs of electrons in VSEPR means that the structure is going to be linear. This table gives the list of structure that you need to know for VSEPR. So we had gone through the simulation where we showed 2 pairs of electrons, and with 2 pairs of electrons all you can have are bonding pairs. So with 2 pairs of electrons, the structure in the electron pair geometry is going to be linear. The molecular geometry is going to be exactly the same, so that's also going to be linear, and then the bond angle is going to be 180 degrees. With 3 pairs of electron, I showed you the 3 bonding pairs, and that's going to be called trigonal planar for both of them with an angle of 120. It's also possible that only 2 of those are bonding and 1 of them is a lone pair, in which case it's still a trigonal planar electron pair geometry, but the molecular geometry is going to be called bent, and the angle is going to be slightly less than 120 degrees. With 4 pairs of electron, I showed you the tetrahedral structure where all 4 of them are bonding pairs, and I also showed you the structure of ammonia where only 3 of them are bonding pairs and 1 of them is a lone pair. And that one, we have a molecular geometry that's called Trigonal Pyramidal with an electron pair geometry of tetrahedral. The angle is still going to be 109.5, a little bit less than that. You might also have 2 and 2. So 2 of the pairs of electrons are bonding and 2 of the pairs of electrons are a lone pair. In that case, again, same electron geometry, but then the molecular geometry is going to be called bent. And that would be illustrated by the structure of water.